So we have a talk by Jyotirmoy Das. He's going to talk to us about the Pulsar search pipeline that they're developing as part of the Spotlight project. So take it away, Jyotirmoy.
Yes, thanks. So hello, I am Jyotirmoy Das. I am from NCRA, a PhD student. I am also working in the Spotlight project, but from the Pulsar search aspect. So this is the block diagram. So you can see the whole Spotlight system. So I will be mainly talking about the Pulsar search part, which you can see here. So there are two part of the pipeline. One is the offline E50 pulsar search and offline FFA pulsar search. So we intend to do it in quasi real time. So in FRB search, where the data will be recorded in real time and searched in real time. But for pulsar search, as the search domain is large, like basically that we need longer computation time. So we intend to do it in quasi real time. And there will be two part. One is the A50 part. A50 part is for the fast pulsar search, where depending upon the sampling time, we'll be searching for pulsars from or more or less from 10 millisecond to 1 second. And for the FFA pulsar search, we'll be searching for the long period pulsar, where the A50 search the sensitivity reduces. So for currently, we are dropping 160 beam in the disk, and we are doing the search. Later on, when there will be more number of beams online available, so then we have the capability of dropping maximum 200 beams to do the pulsar search. So that time we will be selecting the most probable beams 2000 from the 2000 most probable beams using PulseScan and BBDNet. I will explain this later. And then we will do the search on the recorded 160 or 200 more or less beams. So at first, what are the type of the pulsar we expect to search using the Spotlight system? So the Spotlight system have a commensal sampling time of 1.3 millisecond. So because of the sampling time, we are mostly sensitive towards the normal and long period pulsars. So here you can see this PP dot diagram, where there are two kind of bimodal distribution of the pulsars. So red one are the isolated pulsars and blue are on the binary pulsars. But this red one are the typical, so this upper bipolar distribution are the basically the normal pulsars, and the lower one are the millisecond pulsars, where the spin period ranges from few millisecond to around 30-40 millisecond. So because of the sampling time, we will be sensitive towards the pulsar I marked with this black box. So from around 10 millisecond to around tens of seconds. So this sampling space will include mostly the normal pulsars, along with there are this possibility of finding the double neutron star systems. So those systems will help us to maybe probe the gravitational effect and all. So till now you can see there are around 21 double neutron star systems. So if we can find more number of such systems, we will be able to test the gravity and do the relativistic effect study on the better parameter space. And also overall, if we detect more number of pulsars, we'll be able to fill up the space with better. So this is the introduction. So now what about the Spotlight system? As you can hear, heard a lot, that it is a commensal survey from 300 to 1460 megahertz, and there are around expected to around 2000 beams with the 50% area of the primary beam. So for pulsar search, we are expected to dump around 200 beams to search for the pulsars. And currently we are operational on 160 beams, and we are doing the search on that. But later, when there are 2000 beams will be online, then we'll do the dumping the beam, around 10% of the beam to do the search. And now what about the pipeline? So for the pulsar search pipeline, we have two pipelines. One is from A50, which is sensitive towards the low period pulsars from 10 millisecond to around 1 second. And for the FFA pipeline, we will search for pulsars which is have a spin period greater than 1 second. So now the A50 pipeline. So the final A50 pipeline should look like this. So we have a data from the telescope, and then the total whatever number of beams, 2000 out of 1000, will go through a real-time ranking elimination, because we need the most probable number of beams we can dump to search for the pulsars, because we can do the dumping the central beams to do search for the pulsars, but If the pulsars are sitting, let's say some outside of the central region, then we will miss those pulsars. So we have a tool to do that. And then after ranking the beam, the most probable 200 beams will be dumped in the disk. However, the FRB search will go on real time. And then we have a RFI filtering and then filter bank conversion. Then we will do the search in the astro accelerated package in GPUs. Then we will have elimination of the redundant candidates. And then after that, we expect to do folding on GPUs because the folding is the time consuming part. And then there will be machine learning classification. So how to rank this beam in real time? So for that, we have a tool called PulseScan. So what PulseScan does, PulseScan basically try to scan the data in real time to see if there are any periodic signal in them. So here you can see this is a real pulsar A50 spectra. And what PulseScan does, PulseScan basically creates a box card and scans over the data, the A50 part of the data, to see if there are any periodic signal or not. So what it does basically, if you can see, this is the real pulsar response in blue, and the red one is the Fourier domain Zark search, and the square one is the PulseScan. So Fourier domain Zark search is the very high sensitive search where the period will be most accurate, and it takes a lot of time because it does the match filtering thing. But PulseScan does a box card filtration, and because of that, the period of the pulsar will not be that accurate, but it can scan very quickly. And it is a GPU code developed by White et al. 2024. So if we can use this tool in real time to scan over all the beams, all 2000 beams, to dump if there are some pulsar-like signal in some of the beams, we can take out those beams to store for further high sensitive search. Now, so this is the pipeline. Now I will be mainly speaking about the shifting code, how we are shifting all the candidates and for further processing. First, it will go through the astro accelerator search over the DM trial and all. And then for all the 200 beam candidates, it will go through a shifting code. So for shifting code, I'll go to first the beam tiling. So this is the beam tiling of 160 beam looks like. First, for the shifting, we'll search all this beam independently for pulsar candidates. So first, all of the beam of independent beams will be searched over the DM clustering and SNR cutoff. We will implement some of the constant that the signal has to be present over this DM space and SNR cutoff. Then you will shortlist those candidates, all of the beams independently. So this will reduce as around 90%, 99% of the candidates. And then after that, what we are doing, we will take all those sorted candidates of all the beams, and then we will try to see if there are any signal that is appearing in multiple number of beams. So if there is a pulsar that will appear in some of the beams, not all the beams, and that will have a clustered response. So that candidate will have a spatial cluster and also on the DM cluster. So that candidate will have a similar DM value and will be close by in the spatial part. So that will allow us to eliminate most of the candidates because that is RFI that might have a random DM response. But if that is a pulsar, let's say this middle circle is a pulsar, then it will have a clustered response in the DM space, also in the spatial space. But if that is a RFI, random RFI, that will most likely have a random DM response. So that will allow us to take out the most probable candidates. And then we will have a reduced number of candidates. So here you can see this is the first level filtration where we do the filtration on the independent beams. And after that, there will be around 1.1 million candidates. And after that, if we do the spatial level cluster, then we'll have a on the DM filtration, then we'll have around 4,000 candidates. So after this, we'll do the folding on GPUs, but currently we don't have a GPU package ready. So we're doing the folding on CPUs. And also we don't have a 2000 beams recording on right now. We are recording around 160 beams. So this beam is currently being dumped into the data disk immediately. And then we are doing this. So this is the pipeline currently that is operational. And we will update this PulseScan thing here when there are more number of beams. And this Presto folding on CPUs will be updated in GPU folding. So this is the total operational pipeline for A50. And We tested this pipeline in on low SNR pulsar, so you can see the detection. We got the detection at the expected number of beams, and in the central beam where the pulsar is the strongest. And then to talk about the FFA pipeline, so FFA pipeline will be sensitive towards the slow period pulsar where we don't implement the FFT process. So this is basically very similar. So the first stage will be similar. Currently 160 beams are getting dumped, and then we don't have we will not use astro accelerate because astro accelerate is for FFT and FRB search. We will do the presto dispersion on CPUs first and then do the FFA search. So this pipeline is getting developed by Kenil. So then after the FFA search using Riptide, then there will be harmonic filtering and all, and there will be a shifting to do the reduce the number of candidates. So here you can see this is the 76-second pulsar that got processed by the FFA pipeline. So this pipeline is also getting got implemented and currently under processing the data. And then to visualize the final output, we have a web-based server where we will update all the processed data into a particular PDF for manual verification. And if we talk about the expected number of discoveries, so we did a PSR poppy simulation to predict the number of discoveries. So we basically used the earlier 3 years of UGMRT observations to see what are the sky part of the sky we are covering, and using the earlier surveys we predicted the number of pulsars we can detect for the sky coverage and spotlight sensitivity. So we got around detection around per cycle. We are expected to detect around 50 pulsars for 160 beam configuration, and if we include all 2000 beams operational with the beam level, with the ranking of the beams and final folding of the candidates and all, so then in 3 years of time scale the expected number of pulsar discovered is around 1000. So for following up on those discoveries, we are basically asking TOA times in GMRT, and just after the discovery we'll follow up on those pulsar to confirm the candidates and then do the further study. So this is the final summary slide of the pulsar search update. So this is a GPU based end-to-end pipeline has been developed, and this is currently operational, where there are 2 independent pipelines to search for the fast pulsars from 10 millisecond to 1 second, and for the slow pulsars as well. And the both other pipeline is deployed for 160 beams quasi real time. So the future work will be to rank those beam using pulse scan, and then we will have the information of the pulsar as well as the DM in real time. Then we can do precise search using those parameter in the recorded data. And also there is another package is got developed. This is the BPD net that can do a real-time classification of the pulsar to scan for any accelerated signal in the data for real time. So that will also allow us to get a signature of the data if there are some accelerated signals or not. If there are, then we can dump those data. So I think that's all.
All right, thanks, Jyotirmoy. Questions for?
Hi, Jyotirmoy, that was really a nice talk and really interesting. So can you elaborate a bit more on pulse scan?
Yes.
What are stages of, just a brief of it?
Yes, sure. So in pulse scan, what it does basically, so in normal pulsar search, so in FDJS or FDAS, Fourier domain acceleration search or Fourier domain chart search, so it takes real and imaginary component of the FFT and do a match filtering search. Basically, it have a phase information as well as the amplitude information. So it can detect the acceleration and match the, basically it tries to match the data in a filter using a filter that you can see in this plot. So there is this blue curve is the real pulsar signal and the red curve is the match filter. So because of this match filtering, it cannot basically it have to match filter for every signal. So it is time consuming. That's why it takes much more time in acceleration search as well as for jerk search. It takes huge amount of time. But for pulse scan, what it does basically, it takes the real, it basically takes the amplitude of the Fourier spectrum. It does not care about the phase, and then it will define a box curve to scan over the data if there are some bunch of nearby frequencies that can have a pulsar signal. So here you can see in real pulsar signal, this box curve will detect it as a signal, but it will not give you very accurate period. But this box curve approach makes this thing very fast, and also it is implemented in GPU. So it will scan over the data and it will let you know at this DM value, at this approximate period value, there is a pulsar-like signal, there is a periodic signal. So then you can go into that in that beam, in that DM, in that particular period, not very precise, I would say, there is a pulsar-like signal. So then you can dump that data with the information stored that this is my pulsar information. Then you can do a finer search using Fourier domain acceleration or Fourier domain chart search.
All right. I mean, really interesting idea. But I feel like if you have already de-dispersed certain data into certain amount, and then you have taken the power spectrum or taken the FFT of it, and then we are going to repeat the same process again with astro accelerate. You're going to de-disperse data again and then do finer search.
Yes, but like when you are doing in a real time, so that FFT is the dispersion FFT has already been done in for the FRB search, not the DDT and the FFT. So that time we cannot like dump all those 2000 beams. That is the main part, that we cannot like store all the 2000 beams. Let's say there are some pulsars sitting in the very far side in the beam tiling. Let's say this is the beam tiling I have. Let's say the pulsar is sitting in this beam. So if there are sort of total 2000 beams, if you are dumping to only 200 beams, so then you will lose this pulsar. But as we are doing the search in offline, because we cannot do the online search and the high precision search, we can basically, as we already have that information, we can scan in real time if there are some pulsar-like signal. But if you want to do the search in real time, the high precision search using Fourier domain acceleration search, you will not be able to do that because of the time it takes. So it basically scanning the data, then we will dump this beam, ignoring one of the central beams to search for further processing, basically.
Yeah, I mean, fantastic. So I think the block diagram was a bit misleading. Yeah, but really nice. Yeah.
Any final questions? Quick one. Going once, going twice. All right. If not, let's thank Jyotirmoy again.
Thanks.